Hi, I'm John Schmenk, and this is the new horizon of 3D printing. I would like to mention before I start that I did have a partner for this project, Antoine Gagne. However, he was unable to make it today, so it'll just be me. But let's get started. So, 3D printing is an additive manufacturing process where you have plastic filament that is put through a print head that melts and extrudes the plastic and deposits it layer by layer to form a part. And I have a piece here to show you. This was a shark before we pulled it apart during our tensile tests. So you can see there all the layers are rough on this curved surface. So it was printed layer by layer. And some downsides of that are it creates a rough edge. And the grain flows also just in one direction, so it makes the part weaker, like wood, like it's weak on that axis. So we found out about a new method of 3D printing called non-planar 3D printing, where the print head actually follows the contour of the part, so you end up with a smoother surface, and the grain flows in more directions. And so we thought this would create a stronger outer shell in these non-planar 3D printed parts. And our hypothesis was that the non-planar 3D printed parts would have a greater tensile strength than the planar 3D printed parts. We really became interested in this when we learned to use Autodesk Inventor at our school and use 3D printers at our school. And we were familiar with traditional 3D printing, but when we found out about non-planar 3D printing, we wanted to explore the benefits and the downfalls and just compare it to regular 3D printing. So that's how we became interested. And as far as we know, there have not been any studies done on the tensile strength of non-planar 3D printed parts. So as far as we know, this is the first one. So we did some background research before starting our testing. We looked into just tensile strengths and how you read the graphs and things like that. And when starting our tests, we had two groups, a planar group and our non-planar group. And initially, we had 3 sharps that we were going to test for each group. Now, as it turns out, when testing, the tensile tester, which we actually used from our school, Mark 10 Series 2 tensile tester actually, it incorrectly logged some data, and we had to throw out one data set from each group due to this. So our data set was smaller than we intended. But as you can see, I'll show you. As you can see here, this is one sharp that was fractured during tensile testing. Excuse me. We designed these parts using Autodesk Inventor and printed them out on a monoprice 3D printer. We also used Slicer software to enable us to print using this non-planar technique. Each sharp was tested until it fractured to get a full range of data and create these graphs, which you can see here. And these are the results that we ended up with. And as you can see here, I'm just going to use this as an example. This was the second planar test. Here's your plastic region, which is where the part is being stretched, but it will return to its previous state. So it's like a rubber band. Like when you stretch it, it's going to return to what it was before. But here you have the yield point. And so after that yield point, that part is permanently deforming. So that's like when you have a rubber band and you stretch it and it breaks and it's permanently deformed. It will not go back to the way it was before. So here you have some strain hardening until you reach your fracture point there. But the main thing we were looking at here was really just the max tensile strength, which you will see down here. And actually, as it turned out, the maximum average tensile strength of the planar parts was actually 10 pounds of force greater than that of the non-planar parts. So our hypothesis was rejected by our results. We think that further research would need to be conducted to support this conclusion. There are multiple errors that could have potentially led to this, such as I mentioned before, the tensile tester incorrectly logged some data, which could have affected our other tests as well. And another potential error could be delamination, which I'll just use this part as an example. So when the parts are being printed, you can see the layers there. The filament is hot, and as it cools, it contracts, and it can pull away from the other layers, and there's not much adhesion there. And lastly, not sure if you can see this here, but there's an image of our tensile tester pulling apart a sharp. If the sharp isn't inserted perfectly vertically, the axis of force will be skewed and the part will behave differently than it would normally. So we learned, even though our hypothesis was incorrect, we learned a lot from this project. We learned that, as it turns out, the planar parts actually have a greater tensile strength than the non-planar parts. And overall, we just learned about the scientific process. We hope that this research can push forward the frontier of 3D printing and help to expose some of the benefits and potential downfalls of the new non-planar 3D printing. Thank you.